So this was a little bit of a trick question because it's a 2-argument function. You can get an inverse if you you create a function bool to one of these original types, right? Bool to bool to bool, and you apply either true or false. So you can only get one inverse function. Otherwise, it's surjective, right? But you lose information on the way to the 2 Boolean values, and you can't go back. But you can go back in one case and only one case. Moving on. The original one is surjective but not injective. So I have some more examples here of isomorphisms as functions. If you're familiar with Haskell, then you know curry and uncurry. These are isomorphisms that you can go back and forth between. Swap is an isomorphic function that's also, I guess, an automorphism maybe. There are all these other words, endomorphism and automorphism. Endomorphism is a function that goes from a set back to itself. Automorphism. Well, this is like too much terminology probably, and I feel like I created more material than I have time to cover, so I'm going to skip some of it. Getting back to, yes.
Did you say? Sorry, I missed your answer for and or. Did you say that was?
So you can't create a general function that's isomorphic, right? Like you can't go back.
Writing the inverse.
Yeah, you can write an inverse for. I wrote this inverse function, reverse bool. It takes a bool and returns a function, but you have to apply either true or false to it, and then you can recreate the original Boolean function.
I would think the inverse of and would be you take a function from bool to bool as an argument and return it.
Exactly,
Yeah.
Say that again?
You take a function from bool to bool and return to bool.
Right, but if how do you know what you started with? How do you know what you started with? Like if you have true or false, that's false. But how do you know what 2 arguments you started with? Like how do you go back? Because you lose information. You just have false, right?
Your argument is a function.
Yeah.
From bool to bool.
Yeah, I see what you're saying.
Then you have to test it. You have to figure out what
Yeah.
it is. You have to test it by applying it.
Yeah, I mean that's like basically what I did by partially applying it, right? Like same kind of idea. In fact, that's the way you have to do it in order to be able to have an isomorphism. Okay, so I want to actually move into category stuff at some point. So some properties of functions that we like to have. This is familiar at the value level. I hope if you know a little bit of Haskell, you know composition. So composition is important. Identity, these are like laws for functions that we like. Composition, identity, and associativity. Is everybody familiar with composition, identity, associativity, basically? So the same thing will operate when we get to categories. Just as like a brief little funny exercise, composition is probably the most important law that we have in category theory. So you can compose any number of things, and for example, this is an example I prepared for people who like know nothing about composition. You can think of it as any kind of linear process if you want. So I picked brewing beer, right? Malt, mill, mash, boil, ferment, bottle, for me, drink, and regret. It doesn't matter what order you do these things in. You can actually put parentheses around them however you want. And it shouldn't matter, right? You should be able to write a function that lets you go from malt all the way to regret in one move. This is at the level of functions, but this also operates at the level of category. So now we get to what is category theory, which is, I guess, the fun part and the part that is hard to explain. So this is like leaping up a little bit from sets. I think sets are extremely attractive because they have elements in them, and we can think about them in ways that are familiar. I mean, if you studied sets a little bit in university or something, or math class, you probably didn't study category theory. You may have studied sets. When I first encountered category theory, it seemed like it was an abstraction or a generalization of sets. Now I don't think this is a very good definition. I think you can probably describe a category more like a universe that has certain laws in it. I mean, you can say collection. We sometimes say a category is a collection of objects, but that makes it sound like a set, and it's not a set. I mean, the words are not really as useful as kind of the concept that you need to grasp mentally to understand what a category is. I mean, you can say like realm or space. I mean, universe is not necessarily the best word because it gets used elsewhere to mean other things. One of the problems with sets is that you get this paradox where you can't have the set of all set being a member of itself. But this is okay in category theory because you can just say that there are large categories and there are small categories, and the large category can contain the category of categories, which is a small category. So anyway, I'm like bloviating a little bit. Here are the important terms. So category, right? This mathematical world where we have objects and then laws that determine how they relate to one another. So we don't like to think of them as sets. We can have categories where the objects are sets, but that's one. And then this is also the category that's interesting to us as programmers, right? The category of sets. And in fact, I think I should do maybe a little bit more scribbling to explain what I mean. So when we go from sets to categories, I can have various sets. This is like what I do at home when I take a shower in the mist on the mirror. So we have some sets, and then I want to have the category of sets. Actually, we just call it, set, right? This category of sets, and we squish the sets down into just these points. And we call these objects. I mean, this is an unfortunate term if you're a programmer. Obviously, it has nothing to do with objects the way we think of them, but these are just not elements, because element sounds like set. They're just like things in this category. They obey certain laws. And the arrows actually come along for the ride. So when you're writing a function, you have to have all the arrows, right, mapping from one set to another set. You have to map everything. But here, these arrows just get, like these homomorphisms just get turned into arrows between sets. And if your objects are sets, then you probably have a lot of arrows. I mean, it's kind of a undifferentiated mass when you have the category of sets. But you're collapsing this pattern. And actually, one way of thinking of an object, not as an element, some kind of abstraction, some kind of pattern. And I said before that the arrows, the functions, are structure preserving. The arrows are the structure. The arrows are what are important. I think when we think of sets, we care about the elements. And when you're programming, you probably care about values. In category theory, I would say that we don't care as much about objects. We care mostly about the arrows, right? So if you have some category and you have these objects, all right, if you're a programmer, you like to have patterns. So we can't actually look inside the objects in category theory. This is the part where you sort of have to like level up your abstract thinking. Like hidden inside of this object is some mathematical structure. It could be a set. It could be a group. It could be a ring. It could be some dynamic system like this. It could be, it could be a lot of different things, and we don't care what it is. It's some kind of pattern. It's some kind of structure. If you recalled my little diagram from before, where I said, a function is like an image of the first set and a second set. This abstraction is carried up into the category, and then we don't even think about it anymore. The laws of this one's even worse. The laws of the category kind of hide this away for us. We abstract over it. So then we can get arrows between things. And whenever we have an arrow, I mean, if this is the category of sets, then the arrows are functions, but they're not always functions. Generally speaking, as programmers, we're dealing with functions, so it's okay to think of them that way a bit. But we're carrying structure whenever we map between arrows. And let me make like a simpler one, actually, which I think just 3 objects is good. And actually, we can start with this empty category. This is a category. I suppose you can call it 0. It's a category with no objects and no arrows. Kind of boring. It turns out to be interesting in some other area of abstraction. If we have time to talk about terminal objects and initial objects, I don't know, maybe. The category called 1, which is a category with one object, also seems a little bit boring, but the category with one object is actually a monoid, which are interesting if you're doing functional programming. Maybe these will come up again later. We can have a category with 2 objects, and we can have an arrow going from one to the other if we want, and back if we want. We can have a category. We just call these things 1, 2, 3. So this is where things are a little bit interesting, I suppose. If we have some category with objects like this, A, B, and C, I should be able to go, did I do this right? No. Let me try again. That's what I get for thinking of things backwards. Okay, so if I can go from some object A to some object B, and I can go from some object B to some object C, then automatically by the law of composition, I have to be able to go from C back to A, right? This is the same as, right, in Haskell. If you're working in a programming language, this is composition. What did I do?
No, in the diagram.
You can't guarantee you can go from C to A, and you can go from A to C.
Oh, oops, sorry. That's what yeah. Thank you. Better? Good. So if I can go from A, yeah, exactly. If I can go from A to B and B to C, I must be able to go from A to C by the law of composition. In addition, every object, we don't usually draw them because we know that they're there. Every object must have some kind of identity. Yep. Like that. So this is just an arrow from the object to itself. So obviously you can compose using these identities as well. So this is also why we don't really care about objects, because you can describe objects by their identity arrows. And you can just ignore objects entirely and just think about arrows. And I don't know, for me this is one of the more difficult and profounder insights of functional programming, and in some way category theory helps bring that out a little bit, that we care more about functions and what they do and using them as data. You could say that functions or arrows or morphisms are data in a category than we do about objects. We don't care about objects. We don't care about elements. We care mostly about how they're being transformed in computational terms, because this happens in time, whereas in like the mathematical world, time is not necessarily an issue. Right, arrow map morphism. Okay, so that was like a very, very broad introduction to the categories and the basic concepts. Are there questions? Can I clarify anything? Yeah.
On the far right chart, you have the A, B to C and the arrows. You got a circle. Is the circle describing a set or a category?
The circle?
Think of set, or then I'll think of category.
This?
Yeah.
This circle.
Right.
That's a category. Yeah. No more sets.
I think it's confused because it's a set.
Yeah, it's the category of sets.
Can I basically have multiple arrows from object to object? Like more, like.
So yeah, let me just finish answering that question, and then I will try to answer your question. So not every category will have as its objects sets. So in this category, the objects are sets. If you think of, for example, Haskell types as sets, you can think of the category, you can imagine a category in which the objects are types and the arrows between them are functions. And this is called Hask. This actually is something, this is a real thing, you can read about it. I don't think it's probably not a perfect representation of category theoretical ideas, but I think it's good enough, right? Hask instead of set, and then the objects are types, and types can also be thought of as sets. So kind of, this is the hand wavy part, same. And then there was a question about arrows and which arrows you can draw over here.
Yeah.
What did you ask?
I mean that we have an object can have like multiple arrows from itself, not only like these. Like we can distinguish them somehow. Like multiple arrows from one object to each other, because this is always for confusing.
I'm not sure I understand the question. I almost understand it.
If we have a monoid,
Yes.
can we have like multiple
Oh, okay.
arrows from?
You want to talk about monoid. So monoid's important. I mean, it's important. It's also kind of boring, right? Because it doesn't tell us very much. I mean, it's useful because we get some algebras out of it, right? In a certain sense, you can actually think of a category as a generalization of a monoid if you want. And like a monoid is this special case category. I wasn't going to talk about monoids, but since you brought it up, or I wasn't going to talk about them right now. So to have a monoid, what do you need? You need some kind of identity function, right? And for multiplication, this is 1. For addition, it's 0. And for other kinds of structures, it's other things, like lots of possibilities for identities. And then you need some kind of operation, and sometimes we represent it like that, right? So it's usually this A to A operation. In Haskell, what is A to A to A? So it's gluing things together, but getting back to the same object. That's why there's only one object in a monoid. That's why it's kind of this undifferentiated mass of stuff. So you always have the identity arrow. If you want to have some other arrow like that you're composing, you can have, yeah, there are like many, I don't know, infinite arrows, but they all kind of look like that. And you can, but we don't put them in because you can't draw them all, but they're understood. But this is maybe why dynamic programming languages can be problematic, because they are essentially monoidal in nature, right? You can kind of combine anything with anything, sort of. We would like to have a little bit more structure. We would like to have more than just one object for the most part. So we kind of want to, we'd like to have this category of well-defined sets that are types, right? So these are all types. Maybe this is int, and I don't know, etc.
Can you maybe talk about options since it's so common? Like, what is option in this?
Actually, and also, before you get into options, can I jump in and actually say, as a developer, why you would like Monoid?
Please.
So, in 1,000 lines of code, most of it pure script, for a place that does 60 billion transactions a day, they are deploying all of their software, like whether you would deploy it to a pod or like all these different versions of 15 different services in about 1,000 lines, because it's basically an immutable monoid. These guys are deploying all of this stuff worldwide on a monoid. So monoids are, you take two things and you have an association with them, and then you still have the same type of thing. So if I have a JSON object and I merge it with another JSON object, I still got JSON. Like jQuery is so amazing because it basically brought monoids to the masses. Like once you've got a thing into jQuery, you can keep doing operations on it over and over and over and over and just string things together forever.
Mm-hmm.
So I think monoid, and I did not do a good job explaining this, but monoids for developers is incredibly valuable, to the point of it's almost as valuable, or it's in the same realm of like monads are valuable. But basically, if you have a monoid in your code, it means you can just keep stringing stuff to it on and on and on, and yet still treat it as if it's that same thing. And configuration languages, stuff like that, it pops up all over the place. And if you want, I did a sucky explanation to explain that, but I'll explain anything else with examples. Right.
I hope you didn't think I was attacking monoids.
Oh, no, not in the least. I see, but it's so easy to be like, oh, why is that useful? And that's the one that I think is really useful once you start seeing it in code, because it pops up everywhere.
Yeah, monoids are fine. It's just bad when you only have a monoid. That was the only point I was making. But thank you for your comment. Yeah, do you want to respond to that, Vincent?
No, I have a question around like multiple arrows going to the same object. When you're like working in a category, do you just kind of collapse all those arrows into one and just think about the one arrow, or do you like think about multiple arrows coming out of one object going into the same object?
I mean, I guess it depends what you're trying to accomplish. Okay. I mean, if I have some arrow A to A to A, I mean, this is two arguments, right? I mean, I can sort of just do that, and I know I'm going to get there. I mean, we don't always draw these things, right? This is just for explanatory purposes. If I had some A to B to A, right, A to B to A, it would be like that. In the case of monoid, it is just always going back to the same object. Anyway, this is like more of an intuitive thing. This is also why you can say that a monoid is like a special case of a category, because you do have a kind, like you do have this this idea of, this is essentially multiplication or product. It's not multiplication like multiplication of numbers. You can certainly have a monoid that represents multiplication, but you can have monoids that represent all kinds of different ways of sticking things together. And then this is like the generalization of that. And then composition is the generalization of that, since composition is like multiplication of objects. One of the annoying things about category theory is you end up finding out that thing A is a generalization of thing B is a generalization of thing C, and the generalizations just keep piling up. That's kind of why I started with very simple stuff today. And someone asked about option, and good question. Okay, so we covered category, covered object, arrow. Now we get to functor. So functor, I think, is the most important concept in category theory. I mean, I shouldn't say things are most important concepts. I'm going to get yelled at by somebody. It has been said. So I mean, originally category theory came out of the study of topology, and then it was realized that it applied to many other things. In fact, it was realized that it applies to, I think, every area of mathematics, and it's ultimately a generalization of all mathematics. I don't know how hyperbolic you want to get. If you think of mathematics as a way of describing things that we know about, then category theory is like the mathematics of mathematics. Therefore, it's a way of describing relationships between all things that we know about. I mean, that's like pretty general, right? It's like everything. I think some mathematicians would probably dispute that a little bit. It has been said that the reason that they invented category theory was to define functor, and the reason they defined functor was to get to natural transformations. So I don't know who asked about option. I'm assuming by option this is like Haskell's maybe. So this is a functor. So this is like the next thing that we can talk about. I suppose, why not? I'm not a professional category theory explainer. This is the first time I've ever done this, so I don't mind being a little bit fast and loose as things come up.
Technically, you are professional.
Professional what? Thank you for your contribution. So let me think. So I have some, let's say, some category C with some objects, and some category D with some other objects. I can draw, so these are categories and not sets, right? Between the objects, I can have arrows. I can also have an arrow from C to D. All right, and an arrow from one category to another category is called a functor. So we started with function, and then morphism, right? And a morphism is a generalized function, and a functor, I guess, is a generalized morphism, because now we're talking about arrows between categories. So the neat thing about arrows between categories is that, like all arrows, they're structure-preserving maps. So if you have a list of things, or an optional type, or a maybe, or whatever, that is, so I said the arrows are what are important, right? The arrows are the structure. And the functor actually carries the arrows from one category to another category. It preserves your mappings. So if you're mapping objects in this category to objects in this category, then you get the same idea, the same like image from one to another, if this is like, I don't know, some functor f. And this is an important concept in category theory, this idea of mapping between categories. I don't know how many languages support this as a computational concept. I generally think of it as as something like a higher kind of type. So we have higher kind of types in Haskell. I don't know, do you have higher kind of types in Scala? Okay, that's super. So you kind of get this kind of functionality for free, right? You're packaging up some information in this higher order kind of function, and you're passing it along. And it preserves the structure at every level. It preserves the relationships between the types, and it preserves your function. So it maps objects to objects and arrows to arrows. Yeah?
Can you give an example
Of what?
of the functor mapping from category to category?
Yeah, actually, I think I have some exercises for that, which maybe we can just do right now. Let me see. Oh, yeah. Also, we have functor laws. These should look very similar to the laws for composition. They're the same. They're just with like one level of abstraction up, like identity and composition carried along by the functor idea. We haven't gotten to that yet. So actually, we have exercises here. Maybe, again, you can work together with each other. Like rather than me just like giving you some example, these are examples of functors, of things being mapped into functors. And these are actually very simple exercises looking at these functions, which use some of the same material from the first exercise file. And I can repeat that if anybody needs it. I can just cut and paste it or something. The idea here is just to write functor proofs for the composition of maybe lunch and lunch maybe. And you should be able to chat with each other to figure that out. And then I think it will become clear that it's really just the same thing. Like the functor is the same thing as a function, just at a higher level. So why don't you work together on that? It's just essentially proving the functor laws using these functions. And these functions themselves are examples of this kind of mapping from a category into a functor. So chat with your best friend and or find a new best friend. And just very quickly write some functor proofs. So these are some answers that I'm just testing on random data just to demonstrate. I mean, obviously you can't just type this into Haskell and have it work because Haskell can't check that for you. So you can just pass some data in and then you can check it and verify that it's correct. So again, the structure is being preserved. I wrote a better functor diagram for you while you were doing that because we are running out of time, I see. So again, this idea of the functor is so important in category theory because, I don't know, for me it was a little bit mind-blowing to think of, I mean, I can imagine mapping from objects to objects. That makes sense, right? I draw some dots and I draw arrows between them. I can grasp that. But category theory kind of entails drawing arrows to arrows. And then I thought that was really unfair. That's like too hard. And this is kind of what functor is doing. So for some category C and some category D, let me back up for a second. This is also going to be an unfair statement. So when we're dealing with programming, you can think of things as functors. It's fine. In Haskell, it kind of depends how you implement things, right? Because everything is just a function in Haskell. We're faking everything in category theory with functions, right? You're not really working with functors in some mathematical sense, like in the abstract, but they're equivalent in an operational way. But you're also not generally mapping from category to category. In Haskell, functors are endofunctors. I mean, some of you have heard this. It doesn't matter though. I mean, you could imagine that D is actually just C again, right? It's the same category mapping to itself. That's all an endofunctor is. Like an endomap is a map from one set back to the same set. So an endofunctor is a functor from a category to the same category. So denoted here by F. So this F can be maybe, it can be list, it can be whatever your functor happens to be, right? Like list is convenient. We like list because it makes it look like you're dealing with containers. I think it's controversial to call functors containers. I mean, I kind of have a whatever works for you mentality about these things, as long as you're not complacent with your the way you like make things concrete in your mind because you have to. Never get complacent with that. Never assume that you've got the right idea because then you move up to a higher level of abstraction and the idea doesn't really work anymore. Anyway, I have some function f that goes from A to B, and when I map it using the functor, I'm mapping it into this category D, and now I have f of A to f of b, but the a to b relationship is preserved. The arrows are also mapped and they're preserved. And in addition, composition is preserved, right? I can still do this. And identity is preserved for each of these. So you get the image of one area. I mean, we're not using sets anymore. We get the image of C in D. It's like embedded into this other category. So functors, just like sets, embed structure, right? It's a structure preserving map. A function is a structure preserving map. A functor is also a structure preserving map. Are there any questions about this or things I can clarify?
Is this mapping from one category to another category, or from one object in a category to another object?
Okay, I mean, it's mapping all of it. I'm mapping objects to objects and arrows to arrows. So objects in one category to objects in another category, and the arrows come along for the ride. That's what the functor is doing. I mean, you can certainly just embed an object. I guess you can embed an object into, well, I don't know, put it there, like that.
So C and D are categories then?
Yeah, C and D are categories. And this can also be C. It can be the same category. You didn't like that.
I like it more as D.
Right, well, yeah, because like C to D, that seems like two different things, right? But I mean, if you're familiar with, the identity function is A to A, right? So it's just some A going back to itself. I mean, you can also have a C going back to itself. So there's no problem having a C to C. This is a functor, this is a function. They're both arrows. They're both morphisms. The functor morphism is just a generalization of the object morphism.
So you got something like the ID where it goes from A to maybe A.
Then you have a functor.
Right.
Because you're embedding A is this pattern, right? The object is a pattern. There's something inside this A, and I don't know what it is, and I don't care, but I'm going to embed that, and I get to take it with me, right? I'm going to embed it into the functor, right? And the functor preserves that structure. I mean, you could embed, like I said, list is a good example, but you can also say, maybe A is also a structure. You can embed that in further structure. You can embed that in more structure. You can stick this inside of a just if you want. And at every level, you're preserving the connections. You're preserving the structure. You're preserving the arrows, the identities, and the composition. That's why when you're working with these values, you can put them together and take them apart again, right? You can always get inside and do something with the value. You don't always have an isomorphism, but you always have the structure. And that's how you work with these things in Haskell, for example. That's kind of, I can't really speak to Scala. I don't know. I assume it's got to be the same thing because the concepts are equivalent. Does that make sense? Does that work for you? I know it's a little weird because it's not just mapping of objects, right? Because you're also mapping relationships. Any other functor questions? Yeah.
Are functors always bijective?
Are they always what?
Bijective.
Are functors always bijective? I don't think any arrows are always anything. Unless someone else wants to respond to that. I don't think you can say any arrow is always.
The answer is no.
Yeah. I'm trying to I'm thinking there are many instances of categories where there are no isomorphisms. Like I don't know, maybe a post set, partially ordered set. You can't go back if you have an A to a B. That necessarily means that A is less than or equal to B. So then you can't go from B to A. I assume that the same logic holds at every level. So it just depends what you're working with. Yes?
Is it a one-to-one mapping?
Is what a one-to-one mapping?
Like the number of objects in C is the same number of objects in D.
Okay. So if you have a functor of C, are you mapping every object into D or whatever category?
Like an A and B go to one object and the size changes the shapes.
I think you're actually mapping everything. I believe so. I believe you're mapping everything. If you have a functor, you're mapping everything because you're preserving all of the same relationships. Does anyone have any better idea about that? Yeah.
I think you're preserving the so-called home set, and there are special cases where you can easily map to everything just to one object, which preserves the transformational hull of the inner objects. I'm not a category theorist, but I just...
I am? Say it one more time. Can you say it without saying hom sets? Because I don't want to talk about that.
Okay. But I think you can create a functor which maps the entire input
Yeah.
to just one morphism and one object. I believe you can define such a functor, and it's a valid functor.
Mm-hmm.
And in a Haskell, you would visualize it as a constant function or something.
Mm-hmm. Okay. Do you want to draw it?
No.
What would happen if you have a functor that maps everything to nothing?
A functor that maps everything to nothing?
Yes.
What is nothing?
I mean, like instead of the
Yeah, you have very simplified maybe that has only nothing, one object like this.
Yeah, you could map it back also.
Oh, you mean like capital N nothing? So you want a functor that maps everything to nothing? I mean, I guess you can do that. Nothing is, nothing in category theory terms is like this terminal object. It's just sort of like nothing. You're talking about this nothing. You're not saying like nothing is an abstract idea. You mean like nothing, like that, right? So this is a set with one value. It doesn't matter what your set with one value is. I didn't really emphasize this idea of isomorphism too much, but isomorphism is kind of like same shape, but not same value. So these kinds of things, they all have the same shape, right? It doesn't matter if you're talking about unit or nothing, or you can, whatever, it doesn't, orange, you can, Steve. It's just a set of one thing, so it's just, we just say actually this, nothing is a special case of that, or I don't know, it's a synonym for that really. And yeah, you can map everything to it if you want. In fact, for every, in a category, I didn't talk about terminal objects and initial objects because, I don't know, they're not connected to anything that interesting, relevant to programming that I could think of. But the definition of a terminal object, which is what this thing is that in any category that has a terminal object, every other object has a unique arrow or morphism to that object. Is that interesting information for you? I don't know. What can you do with that? I'm not really sure. Actually, I don't know. Let's see. Every object has like this thing. You can actually use this as a kind of selector function. Let's see. A to unit to A. Yeah, this is what I'm thinking of. So in some set of things, this function, like if I have this function, that's essentially like picking 5. So if you're thinking of 5 as just an element, I mean, you can also think of it as a function from the singleton set to 5, right? And this is just like some nothing dummy value. We don't care what it is. It just like picks something out. It's just an idea. We also have the initial object, like void to A. So void to A and A to, we call this unit. These things are like isomorphic. You can't actually implement that, but it exists as an idea. I think I somehow got way off track of your question, though. Yes, you can map everything to nothing.
Valid functor, we just map everything to nothing.
Yeah, why not?
Not in that type, but if it's unit.
Yeah.
Kind of in general, a functor is just mapping one category to another category. So if we look at Haskell, we're biased to think about Haskell functors, which are Haskell to Haskell. But what Steve's pointing out here is you can just pick some other category, which is super degenerate. You can define a functor that maps everything in your first category to that degenerate category. And then there's not about that. There's not nearly enough information in that degenerate category to get back to where you're going. Which is what he's pointing out there, but it's going to, the Haskell functor will bias you to think of that, but you don't have to.
Yep. Does that help? Yeah.
You said you were preserving the structure.
Yeah.
So if I have like maybe lunch on the left side and I use a functor to map it into a list of lunch, is that a proper functor?
Yeah.
Does it have to be
Yeah.
a list of maybe of lunch? maybe hard to get deconstructed.
I mean, it doesn't matter. You can you can map anything into anything. Like I said, you can have a functor and you can map it into another functor and you can map it into another functor, and at every stage the structure is preserved. That's totally fine.
So what you're saying is when you're applying a functor, the function you use to convert the element from one type to another doesn't have to be isomorphic.
No. The F map is the functor, by the way. So this F thing is the structure, I guess, is the type. From the questions I'm getting, I'm sort of wondering if it's worth going into natural transformations. That's what happens when we take all of the functors from like some category C, and we actually can say, okay, these functors are now an object of some other category, the category of functors. And then we can have morphisms from functors to functors. Why not? Why not be completely out of our depth? So if you're studying category theory, you probably have to read a lot of books or watch a lot of videos or whatever. And you might be so fortunate as to get up to natural transformations. This is a difficult concept to explain, but it makes a pretty picture. So I'm going to try. So let's say we have in some category A to B, to remind myself even how to do it, like this, some category C. I can actually map this into another category. I think we just saw the same thing. Right, this is FF. This is FB. I can also have a different functor, right? There could be different functors mapping this category. We've already seen maybe and list as two possibilities. So you can pretend that list is F. I can have some other functor G, and this is doing the same thing, right? I get from G to A via G to F to GB, and this is okay. So one of the neat things that you may encounter in category, like one of the first things that you'll encounter in category theory that's really neat, does apply to programming, is when this happens in some category, you actually get kind of for free an arrow from FA to GA and FB to GB. And these are the components of the natural transformation, we say. I've seen them described various ways, like eta, for example, like eta A. Once you start getting into Greek letters, it becomes intimidating, right? The point is, like, you get this nice little diagram that has this commutative property. So if you're trying to get to GB, composition is preserved, right? It doesn't matter what order that you do things. I mean, it's the same thing, again, at a higher level of abstraction. You can go from FA to GA to GB, or FA to FB to GB. It doesn't matter if it's an endofunctor or a regular functor. And this is a natural transformation. It's natural because you get these components. They like naturally fall out of this relationship. You just get them because of the categorical laws of composition. If you're interested in pursuing this idea, or if you're familiar with the notion of theorems for free, this is why we have polymorphic functions in Haskell, I think it's safe to say. So polymorphic functions in Haskell are often natural transformations in disguise. So one of the things you could get out of category theory is some better understanding of its basis or its fundamentals in mathematics, if it's interesting to you. And polymorphic functions are something that we use often enough that that kind of understanding or that conceptual basis is worthwhile. So what is actually happening here is we have a category called, like, let's say functor C. This is a category, and we're mapping that category to G. Let me say G of C. We'll make it like the same thing. So our abstractions now are functions, which are arrows from sets to sets, morphisms, which are arrows from objects to objects, functors, which are arrows from categories to categories, and then natural transformations, which are arrows from functors to functors. And it gets very hard to hold in your head. You essentially have to master the abstractions at one level, and then when you feel very comfortable, you just go to the next level. I don't expect in a 2-hour workshop today, all of this stuff is going to make sense immediately. This is kind of just a taste of category theory. Everything works out the same way, though, in the end, because a category is ultimately very simple. And this is why it's hard to discuss category theory, because a category is simply some objects that have arrows between them, and the arrows compose, right? It's some object that describes laws that are based on composition. And you have to do more interesting things before it becomes useful for explaining anything else. But when you're just explaining what category theory is, that's sort of like the challenge. You're dealing with just like generalizations. That's why I would say category theory is, I mean, theory, what is this word theory? It just means a way to look at things, right? So category theory gives you a way of looking at your programming if you want, or a way of looking at relationships between things. It doesn't just have to be in programming. I would really emphasize structure-preserving maps most of all, and sort of use that as your maybe the point that you're trying to make when you're talking about maybe functional programming or category theory and its relationship to functional programming, right? It's a theory of structure-preserving maps, and functional programming gives us structure-preserving maps, and it makes it much nicer for us to code by preserving these structures and actually having some patterns in what we're doing, and not simply write arbitrary code. I think a lot of code that is written tends to be arbitrary. You don't have to write code with some strong categorical theoretical basis behind it, but you can at least understand that a lot of those guarantees that you get from doing FP, they're for free. The laws, they come from this, and they're just nice to have because you don't have to think about them. Category theory and mathematics in general simplify things, even if to us it seems complex. It's just, I think it's just unfamiliar. Anyway, I want to conclude that speech by offering one more exercise. And we only have a few minutes left, so I can probably just leave you with this. And this is kind of like expert level exercise. So a typical natural transformation, I looked for a lot of examples. I mean, you can actually find a few in my exercise files. All of the examples that I found always used safe head. It's the first one I thought of. I wanted to use something more interesting, and I gave up because this is a perfectly fine one. I think everyone is familiar with this, this function, or at least you get the basic premise, right? We don't like head that we saw before because it's a partial function. So we'd like instead this total function that takes into account bad values. It is a list of A to a maybe A, and because it's a list, because we're dealing with a list and a maybe, we're dealing with two functors. You can see a type of natural transformation above for lunch. Same thing here, right? FF to FG. So this is a natural transformation. You can actually write a proof for this. It's very simple, using the same kind of law with composition to prove it to yourself. And then my expert level problem, if you want to try it out, is demonstrate why this function is a natural transformation, but it's hard to tell that it's a natural transformation. You have to be a little bit clever about it. But there's a way of writing this to be a natural transformation. I guess I'll have to leave that to be a homework exercise. Are there any final questions? Yeah.
So you mentioned that polymorphic functions are often natural transformations. So could you give an example of a polymorphic function that's not a natural transformation? I was just interested in the word often.
Did I say often?
I think you did.
I said always. These are the polymorphic functions. So the theorem for free that you're getting is that this works for any type A. You can't make a special case, right? For any A, this will always work. Like you get this. This is your theorem for free. These components. That's like the sort of magical part. I wish I could spend 2 hours talking about natural transformations. Actually, I don't know if I could. One could. You need to go and read about them and explore them. And maybe this is sort of a boost. This is my only hope for today, is that it's a bit of a boost. So I have a little bit of a bibliography if you want to read more. It's in the GitHub. I wanted to leave off with this question again: what is category theory? So instead of having you sit here and try to write a natural transformation based on the length function, as your final exercise for the last 2 minutes, once again, please turn to your neighbor And each of you to the other person explain what is category theory. 30 seconds or less. And thank you very much.